Welcome to Maths with Bob. Today we are looking at vectors, and we are actually going to be representing complex numbers as vectors. And you can actually think of a complex number, as you know, is a point on the Argand diagram, has a real component and an imaginary component. And this is why we actually start to look at vectors, because when we actually look at a complex number, it has two parts, so it has like two components. Let's actually have a quick look at this idea. Okay. First thing is, okay, suppose we have a complex number here, okay. It has a, as you can see over here and down here, it has a real and imaginary parts. Okay, so when we actually add those two real and imaginary parts together, we actually get a vector to represent the complex number. So let's actually draw a vector in. Okay, so this, okay, let's put it somewhere. Okay, so that vector now is representing the components of the complex number. We could actually call the complex number, okay, z equals x plus iy, okay, the x and the iy being the components, and we could actually say that they actually add to this thing called a vector z. So the vector z here is actually representing the complex number z. The complex number, okay, x plus iy, okay, as components, as I said, x and iy. And when you add those two components together, you end up getting this thing called vector z. So vector z is actually representing the complex number in the Argand diagram. Now this is very important because we can actually use the idea of vectors to help us solve a lot of complex number problems. Well, the first thing is, obviously, the modulus of z is actually its argument. Okay, so if I go mod z, that's the length of the vector. Okay. And let's have a quick look. What is the argument? Now, the argument, okay. Now, the argument of a complex number will be the argument of this vector, okay, inverse tan y on x, or just the angle it makes with the real part of the axis here. So let's actually draw it in. Here we are. This is now the arg of, say, z. Okay, that's the arg of z there, the angle that that vector makes, okay, with the real part of the Argand diagram. That's called its arg of z. Okay. Now, how about we actually start to move this complex number? Let's actually move it further. Okay. Let's just rub this out. Okay, we're going to need to move the complex number. So let's actually move the complex number over here. Okay. Again, it's obviously its length is mod z, but where is its argument now? Well, its argument is, if you can have a quick look here, this is the argument. Now, with arguments, this is the arg now, arg of z. You can see here it's actually bigger than 90 degrees. But its argument is actually measured counterclockwise, okay, or anti-clockwise, okay. And there is the idea that the principal argument of a complex number is between minus pi and pi, sometimes written as capital A, R, G, Z. Okay, but normally we would call, you know, the argument of complex number just little arg z. Okay, now there is a bit about that ambiguity idea which we actually use to find roots of complex numbers. So we can actually, if you watch the video on taking roots of complex numbers, you know that because I can get a complex number, I can just keep spinning it around and around and around, and I'll land on the same complex number. Then there is this ambiguity in what's called its argument. Okay, so let's actually now basically move the complex number down below the axis. So let's actually have a look. Get this one here. Now, I'll just move these around and then we'll delete these. Okay, if I can delete them. Okay, all right. Okay. Okay, so here we go. So mod z is actually still the length of the complex number, obviously, but its argument, you now see, is actually measured in the opposite direction down here. So this is now, okay, this is now arg of z. Okay, now that's going clockwise. Okay, so this is actually, sometimes we say that's a negative angle. Okay, it's going negatively. We could say, if you wanted to, you could say, well, it's a negative of the angle going the opposite direction. Yes, you could say that. Okay, let's actually keep moving the complex number. Let's actually move it across now into, say, oops, no, I didn't want to actually, I want to actually just move it over there. Okay, now, obviously I've changed its length, but its length is still mod z, and I'm just going to move these over here and delete them. Okay. Okay. All right, now where is the argument of the complex number over there? Well, Let's have a quick look. Okay, it's still negative, going back that way. So this is now where the arg of z is. It's, as you can see here, over there in that, if you like, the third quadrant or so. It was a Cartesian number plane. It was, but we can see that the angle's direction is quite important when I'm measuring arguments. Okay, and you'll see this when we start actually looking at when we start adding complex numbers. We can then add vectors, and we can actually subtract complex numbers. We can then subtract vectors. Then we can actually see where the arguments are on the Argand diagram. Okay. Okay, so we'll just, I'm going to now draw some more vectors in. So I'm going to, okay, first of all, let's move this away and delete this. Okay, then actually, let's get this vector. Now, while we're here, you can see here, if I've actually got a vector going this direction, let's actually just draw this here. Okay, let's actually just extend the vector and move it up. Just while we're here, let's have a quick look. Okay, let's actually, okay, so this is, say that's vector z, and then we know its argument. Okay, let's have a look. Its argument is down here. So this is the arg of z. Okay, so say z is going down that way. Now if I change the direction of this particular vector, it would be going the opposite direction, okay? And its argument would be up here. So that would be the argument of negative z, if you like. Okay, if my originally vector was pointing downwards. Okay, so we can see here that the argument of a vector and the negative of the same vector add up to pi. I think in one of the previous videos I may have mentioned that the argument of a vector is the negative of the argument of the negative vector. Actually, that's not true. The actual argument of the negative of the vector and the argument of the vector add up to pi. So there's a relationship there. Okay, so let's actually start putting in some more vectors. Okay, so the first thing is we'll delete these. Okay. Oops, I don't know if I'll try and delete them. Okay. Oops. Can't delete them, okay. Delete, here we go. Eventually deleted them. Okay, so now we're now going to, okay, well let's actually add some more vectors. So we're going to say a z1 and a z2. Okay, now obviously you can see here, let's actually call them, okay, this is z1, okay, its length will be modulus z1, this will be z2. Okay, now these are representing two different complex numbers, z1 and z2, okay. And if I wanted to add these two together, how would I do that? Well, I mean, we could do it, we add the real parts and add the imaginary parts. But in terms of vectors, how would we do that? Well, there's a vector theorem about adding vectors, okay? We go from head to tail, or tail to head and tail to head, and then the actual resultant vector. Let's actually move this one. Oops. Okay, these are stuck together. Hold on. Okay, I think I've unlocked them. Let's actually have a quick look at the resultant vector. Okay, the resultant vector, hopefully we can see, would be this vector here. So that would be, this vector here would be z1 plus z2. So that length of that vector is actually obviously the modulus of z1 plus z2. Its argument, you can see here, is here. This is the arg of z1 plus z2. And you can see that that actually represents the complex number z1 plus z2. So the z1 plus z2 is actually represented by that vector, z1 plus z2. Okay, let's actually do some subtractions now. Okay, so I'm going to, first up, let's see, we'll just try this. Okay, okay, all right, so we're going to do some subtraction. So I don't need this vector. I'll actually just delete that vector. Now we do need to actually change the direction of this vector, and this gets a little bit tricky, but I'll just try and change its direction. I need to clone it. I need to swap it around a little bit, so I need to flip it a couple of times. You can see here a bit of a procedure to get. Okay, so let's actually delete this one. Okay, so now I've actually, you can see here, this is now, okay, it's acting in the opposite direction to Z2. So in fact, this is actually, it still has obviously the length of Z2, but it's actually the actual representation of that particular complex number is minus Z2. So really, okay, so if we want to now work out where, so let's actually delete the moduluses. Try and delete the moduluses. Okay, so let's actually just write on them. Okay, so that is Z1. It's actually going, okay, that's the original Z1, but this is now the actual negative of Z2. Okay, and where is, okay, well, what vector is Z1 minus Z2? Well, that vector there, that vector there is in fact, a free vector. It actually represents the complex number Z1, Z1 minus Z2, or if you like, Z1 plus the negative of Z2. Okay, so that vector there, you can see here, is actually, you can see how powerful this is, that in fact now I've now have a free vector on the Argand diagram representing Z1 minus Z2. And where is its modulus? Well, its length is obviously the modulus of the vector Z1 minus Z2, but its argument, this is the important thing, I think, in terms of arguments, is that, in fact, the argument would be over here. Okay, this is the arg of Z1 minus Z2. Okay, now suppose I actually flipped Z1 instead. Okay, so let's have a quick look. If I wanted to flip Z1, and for say I actually so I'll write it in here. Suppose I swap the direction. So I make this one go down that way, so it starts here and goes down that way, and Z1 now would actually start down here and go that way. Then, so what would happen? Well, in fact, if I wanted to add those two vectors together, we're going to need to change the direction of this vector. So this vector this vector here would actually be going the other way, and its argument would be down here. Okay, so let's try that. Okay, so I've actually changed the direction of Z1. If you have a quick look, I'll just move it away. Okay, I've actually changed the direction, so it's now acting downwards. Okay, so that's negative Z1. Now Z2 now is acting upwards again, so that's ordinary old Z2. Now, if I want to now add those two, so it's like minus Z1 plus Z2, or I'll just rewrite that as Z2 minus Z1. You can see here that's this vector here. Moving away too much, here it is, that's the free vector representation of Z2 minus Z1. Okay, so that's the complex number that represents the complex number Z2 minus Z1. Now, where is the argument of Z2 minus Z1? Well, if I extend it down, its argument now is underneath here. Okay, so this is the argument acting down that way. Okay, so the arg would be a negative direction. So let's actually draw that in. Okay, so where would the argument be? Well, we'd have to extend this down here. So this is now the argument of Z2 minus Z1. Now you might remember this one was in fact the argument of Z1 minus Z2. Okay, all right. Okay, I think we might leave it there for today, and thank you for watching. Bye for now.